welcome back. Second week of Psychoacoustics, and the last one. So a brief introduction, as I said. I've slightly shuffled the sequence of things. I've combined stream segregation with Gestalt principles because they relate. And also, I didn't quite get halfway through last time, so we pretty much finished the loudness perception. So what I will definitely do today is pitch perception, bit of time perception, which is not a huge chapter for us, quite a bit of localization, and that's the main thing, and then we'll see if stream segregation, if we have some time left for it, probably not too long, and probably going to leave out the listening test methodologies, but all of this will remain on the slides, and there is a lot of references after, so for anyone who's interested, you can dig into this a bit deeper. Okay, so the thing that we finished with were the critical bands. I think I made a slight mistake, I didn't quite read it. So this line here is a musical whole tone, which you see is a kind of a line, it's linear on a logarithmic scale. And this one is a third octave bandwidth. So it shows us how the critical bands are somewhere around 5K, 6K. No, this must be wrong. This is the bandwidth center frequency. This is rather strange. Why is this strange? Can anyone tell me? Because our hearing range goes up to 16K, 17K. So I don't know how they measure this, the rest of it. So I would reckon that something is wrong with the scale here. It's a graph from 1961. So I'm pretty sure the scale is wrong here. In any case, in the middle of the hearing range, what we have is the narrowest bandwidths. Okay? Now, I won't spend much time on this, but briefly explain you this one. This is a fairly complex sketch, set of graphs, which explains the threshold of hearing a pure tone, which is in the bed of noise. Okay? So what happens is that in the first set of graphs, what you have is a set of situations where you can just hear the tone. Okay? So this is a spectral plot. So a sine wave is a single bar. This is the amplitude of that sine wave. And then the gray box displays the bandwidth of the noise and the level of the noise. Okay? So you kind of see it there, that if the bandwidth of the noise, now I'm talking about the very first one up there, so if the bandwidth of the noise is quite narrow, then the tone pops up quite quickly. I mean, it can be a little bit louder than the noise, and it's still masked, you still don't hear it, but fairly quickly after it will pop out. Now, as the bandwidth progressively gets wider, you need to push the amplitude of the sine wave further in order for you to hear it. And then at some point, this stops to be a progressive development. So no matter, you see the D and E, they have the same sine amplitude, but the bandwidth is wider for E. Okay? So for a while, we get it so that as you widen the bandwidth, you need a louder sine wave, and then at some point, this ceases to be a proportional relationship. So at some point, you can widen the noise further, and you don't need to increase the sine wave for it to be audible. So it kind of shows that there is a certain bandwidth within which there is interaction, within which the masking occurs more severely. Okay? So that's another nonlinear aspect of this, and here it is graphed, right? So you have different noise bandwidth, A, B, C, D, E, and here is your threshold for hearing the sine wave, and at D and E, you see, we actually flatten out. We don't have this relationship anymore. Okay? So it's a kind of a demonstration of masking right there, which is something that we've finished with, and it actually relates to pitch perception as well. So here is the new chapter, pitch perception. Most important, pitch is a perceptual phenomenon. Okay, frequency is a technical term that describes the periodicity of a waveform. So this is really crucial. Why? Because there are ambiguous pitch sensations. So typically bell sounds are such they have overtones which are not strictly harmonic. So they are not integer multiples of the fundamental frequency. Question, what is the fundamental frequency anyway? So with bell sounds, what you have is typically that you will have different people say they have a different pitch. Okay, so how do you do this test? Well, obviously people don't just call out pitches when they hear them very easily, unless they have a perfect pitch. The way you test this is that you have the test subject control a frequency of a sine oscillator or otherwise oscillator, and you're asking them to tune the pitch of the oscillator to the pitch of the bell sound in this case. And if you have a certain bell sound, you will find that some people tune to one frequency and another set of people tune to another frequency, because that's the fundamental pitch they hear. That's the pitch they hear. Okay, I shouldn't say fundamental pitch, I should say fundamental frequency or pitch. Okay, so fundamental frequency is a technical term again, because it has to do with figuring out what is the lowest frequency in a harmonic series, whereas pitch again is a perceptual phenomenon. Okay, so how do we hear pitch? Well, I said something about active tuning system due to outer hair cells. I won't repeat that. Interestingly, I think I said last time that most of the perceptions can be influenced by many other aspects of sound, and it is a very small amount, but it's measurable, the degree to which low pitches will actually be lower, sorry, I should say, a pitch will lower when you increase the level. Okay? So it's not huge, because otherwise our music wouldn't really work in different dynamic ranges, you know. But it is a matter of fact. Yeah? If you play something really loud, you hear the pitch slightly lower. There we go. Totally nonlinear stuff. Obviously, this is a very, very small degree of noticeable change. Just like with loudness perception, we have the J and Ds, just noticeable difference. So again, a graph that tells you, okay, what is the amount of pitch change that we notice. And then the interesting thing about pitch perception has to do with the phase locking mechanisms. Okay, so I've talked about the tonotopic mapping in the ear. So the fact that the basilar membrane has peaks that depend on the incoming frequency. Okay, so from frequency, from tone, you map to the position. That's tonotopical mapping. And on top of that, there is a phase locking mechanism in terms of the timing of the neurons firing. And this phase locking mechanism actually ceases to function at about 5 kilohertz. But it kind of drops earlier as well, and this is connected to the fact that our pitch perception ceases at 2-3 kilohertz as well. So what do I mean when I say this? Obviously you hear a fixed frequency at 10K, 8K, all these frequencies are available, and you hear whether this frequency has any undulation or whether it's fixed. Now what ceases is your ability to classify it as pitch. Okay? So if you have a 4K tone, you won't be able to find the octave below it. Or you won't be able to compare it in terms of musical intervals, even if you're trained, because actually the pitch perception ceases. Okay? I mean, if you play, anyone plays instruments that go up really high? You might actually discover this just by playing an instrument, if it goes really high, that if you're in the really high notes, it's kind of weird. It doesn't really carry the pitch information as it does in lower registers. Okay? Cool. The other thing that the phase locking seems to explain is the consonance of an octave, because then the peaks of the waveform are actually in sync in time, and with other harmonics you will have certain peaks in sync. So it kind of goes to explain what we call the missing fundamental. Okay, so I'm going to do a little demo of this. That's the lovely tone you've heard a second ago, so trigger warning. So I'll show that to you in a second, but briefly I'll just mention that you can elicit pitch sensation in different ways. So one thing that you might expect is a very narrowly band filtered noise, and it does work. You can create a sense of pitch even though it's not a fixed frequency. And also, if you have a sharply filtered noise, so if you take a low-pass filter and have a really sharp cutoff, right, you will also be able to elicit a sensation of pitch. Okay? So the message here is that the sensation of pitch is a complex construct. Okay? So the ear is not a frequency measurement device, and especially in relation to pitch. Okay? So one of the demonstrations about this is what I'll show you. Another thing here, actually we've tried this one with another set of students where I teach psychoacoustics, and it didn't really work. We almost were in pain because of the loudness, because typically it works better with a loud tone. But acoustic after image is supposedly a phenomenon too. So what you would have, you know what is an after image visually? So if you are in a rave and you have a stroboscope going, and when it shuts off, you kind of see something. Or actually, even now, if I was to put the silhouette here on the screen, turn the lights off, you stare at this, and in the instant when I turn it off, you will suddenly see the after image. Okay, so this is something that happens with all sorts of neurological perception, because your neurons are being stimulated, and when the stimulation drops, then that's actually also something that elicits a sensation. Okay, so a sudden loss of light will give you something to look at, just like a sudden loss of sound will supposedly give you something to hear, which is not there, right, because it's just gone. And typically, if you have this notched noise, so notch filtered noise, you play it very loud, okay, and then you suddenly stop it, you're supposed to hear a kind of an after image, acoustical after image, a slight pitch. As I said, we've tried it, we didn't quite get it to work, so it's probably done something wrong. Okay, so virtual pitch, that's an interesting one. I'm going to show you a little demo of this in Super Collider, because that's the easiest way for me to create some stuff. So what I have here is, first of all, 10 harmonics starting at 300 Hertz. You can kind of see them line up there. Those are the harmonics. And then I can play these. Sorry, that's not that. That's the R. Okay? So those are my 10 harmonics. And then what I can do is I can start to subtract the harmonics starting at the bottom. So this would be my, sorry, that was the first one, this is the second one. So you see what I have there is 9 harmonics starting from the second one. Okay? So the question here is, do you hear the same pitch? This one and this one. Okay? And supposedly you do, I do. I have to warn you that I've primed you, because I've made you hear the first thing. First I made you hear the full spectrum, the whole set of harmonics, and then you kind of expect it to happen. As I said, hearing is largely adaptive. So you could probably even measure the influence of priming. But in any case, if I just remove the fundamental, right, so here I've removed the 300 Hertz, I had all the rest, I still hear the pitch at 300 Hertz. Okay? So that is the missing fundamental. I have all the harmonics except the fundamental frequency, and I still hear the pitch at the fundamental frequency. Okay, so that's the demo, and then I can push it. So this is the full on. This is without the fundamental. So obviously you hear it being thinner and kind of less low frequency, but I can actually remove the second one as well. Want to compare this to the original? Yeah, you kind of hear the same pitch still. Okay, so I've removed 2 harmonics. Let's remove the third one as well. Oops, sorry. So this is without the third one. Still the same pitch? I mean, if you sing this pitch, anyone willing to sing this pitch? Compared to singing this pitch? I mean, it's still the same pitch for me. I don't know about you guys. Okay, I'm going to progressively keep removing these things. I still hear the same pitch. Still. Yeah? Anyone starts to think that that was a different pitch? Compare these two. Yeah, kind of. I kind of tend to think that it's slightly higher pitch. So that's the message. I mean, obviously I can go further. Let's see this one. So you can go quite far. So now I'm actually left with, what is it, 5 harmonics out of 10. So I've removed the bottom 5 harmonics of this harmonic series, and I still get the pitch sensation of the fundamental frequency, which is quite cool. And actually, you can do this experiment even further. So what you can do then is you can put it in a context. So if you make a melody out of these, if you make a melody out of these things, then you will even be able to have a single sine wave left and hear it as a different pitch. Okay, so if I go to a single sine wave here, you will actually say, okay, now it's not that pitch anymore. But if I put it in a melody, which means that your expectation is such that you are waiting for that very pitch, and you get just one sine wave, which is one of the harmonics, you will hear the pitch related to the fundamental frequency. Okay? So it's a fairly strong phenomenon. Now, why does this happen? Well, I said that it has something to do with phase locking. So what I want you to observe now is the waveform of these things. Let's just take a scope of these things. Okay, so here is my scope, and what you see there, actually it has to keep running, is that no matter the fact that I removed the fundamental frequency, the actual period, the period of repetition still relates to the fundamental frequency. Okay? Because if you think about it, all those harmonics, they actually line up at the fundamental frequency. Okay? So I won't go further into this, just because there's plenty of other things to do, but the message here is that with pitch perception, what we get is a whole lot of funny things, yeah, including acoustic afterimage, virtual pitch. You hear a pitch at the frequency which is not present in the stimulus. Sharply filtered noise creates a sensation of pitch, and that's about it as far as the tricking your pitch perception goes, to include the bell sounds. Okay, so in describing the nonlinearity of pitch perception, what we have is the Bark scale. I won't go into great detail here. it is a scale that is attuned to how you perceive pitch. So as you know, when we tune a piano, what we do is we take octaves, which are doubles in frequency, and then we divide them in 12 equal parts, not by division, but by the 12th root of number 2. I won't go into this now, but in any case, we divide it to be equal multipliers, not equal adders on the Hertz scale. And that's quite good. That's quite close to how we perceive pitch, but it's not really accurate. Okay? So if anyone wants to create music which is more related to how we hear pitch rather than how we calculate maths of logarithms and so, then you could actually do stuff with bark scale. Okay? So in bark scale, one bark is width of one critical band, and above 500 Hertz it comes very near to the logarithmic scale, so to the way we tune instruments and consider musical intervals. But actually below 500 Hertz it's actually a bit more linear. So we hear things differently. Obviously, if you're a trained instrumentalist, then this phenomenon is not really crucial because you learn your intervals in the lower register like that. But it typically can relate or allows to say something about why it is not always crucial to tune the bass perfectly. Why a double bass player has a bit of leeway to, have some detuning, some issues there, whereas for a higher pitched instrument that would be much more severe. Okay, so that is about frequency perception. And now briefly about time perception. So as I said, everything about hearing is nonlinear to an extent, and similarly the time perception as well. We have a subjective unit for measuring time. Okay, so another set of experiments allows us to measure what you think you hear in terms of duration rather than, kind of adjust to the grid. And we have a unit called Jura. Not very popular, but just worth knowing that typically everything, once we measure it, is not linear, not logarithmic. There's always some strangeness about it, and we typically invent units to describe these things. Why do we do this? What's the funny thing about temporal perception? It is that the duration, the subjective duration, decreases to be less than what it actually is below 100 milliseconds. So you could say, well, that's a bit short anyway, 100 milliseconds, tenth of a second, not much going on there. Obviously, I'm not able to, assess the exact duration once things are so short. But, it can be measured, and it is a matter of fact that you are fooled by these very short sounds in terms of what you think, how long do they last. Okay, few other things about time perception. You can not distinguish a gap of about 2 to 3 milliseconds in a broadband noise signal. Okay, so if I didn't code this, I don't have that much time here unfortunately, but it should be an easy test. You can even do it in your little audio editor. Take broadband noise, take pink noise, cut out 2 to 3 milliseconds, make it silent, listen to it, and you won't hear it. Okay, so we're just not measurement devices. That's the clue here. So, any ideas? What would be a crazy idea for example, for compressing audio? I mean, if I claim that I can erase 2 to 3 milliseconds of sound, how many samples is that on 44 kilohertz? Well, it is about a 500th of a second. So 44,000, let's say 50,000 by 500, it's about 100 samples. Am I saying that right? 10 samples? Probably 10 samples. So what I'm saying is that I can remove an amount of samples and you won't notice. So if I do this progressively, I can reduce the bandwidth needed to transmit audio. But obviously this doesn't work. I mean, it's an exercise in coming up with funny ideas, because once you have a repeated gap, it's different, and once you have something else than a broadband noise, you're likely to notice it as well. Okay? So the thing about psychoacoustics in general is that it is scientists playing with analytical tones, with sine waves, with noise bands, and stuff like this. And, you know, it is good because it allows you to exclude variables in your experiments, but typically it's not real-world scenarios. Okay, so we operate slightly differently with actual acoustic sounds. Okay, other things to say about time perception is that simultaneous events and events that have a very small difference in what we call the onset time. So technically we have a term that is onset time interval, which is the amount of time between the two starting, between the two onsets. If that distance, if that time duration is rather small, what you get is that you don't hear which one came first. Okay? And actually, if you're a percussionist, typically you assess the flams, because a percussionist can do this better in terms of which one came first. So flams, like short time duration hits with two sources, they actually do it by timbre. So if you learn the timbre of two different flams, you will know which one comes first if you're practiced. But if you're not in a lab setting, you won't know which time came first, which sound came first. So there is something to say about this temporal window of perception. Okay? So it seems to be the case that you don't get to hear events as they happen, but you have these windows, these temporal windows that kind of, you know, sort of a lower sample rate at which you get a sensation of a sound happening. And if something is very close, you just don't know what happened first. You hear that two sounds have happened, yeah, but you don't know which one happened first. Okay? Another thing relates to time perception is when things start to speed up. So typically more than 50, maybe 20, maybe 25, it really depends on your training and the kind of sound, you tend to stop perceiving separate events. The events tend to perceptually fuse, which is also the case with motion picture, which is a misnomer because there's nothing in motion. When you watch a movie, you see flickering pictures, one after the other. And the fact is that the correlation between these and the speed of flickering makes it such that you're fooled into seeing motion. There is no motion on the screen. It's a set of images in fast succession. Okay? So the funny thing is that this threshold, you might know that the sample rate for flickering frames, the frame, how do you call this? FPS, frames per second, yeah? That is quite close to the threshold of fusion of auditory events as well. And that is the onset of the sensation of pitch. Okay? So if I have impulses that happen 10 times per second, you hear it, tuck, 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 tuck. You start to speed them up, then they start to fuse into this kind of a gritty texture, and then at some point you start hearing a low frequency pitch. Okay? So the message here is that pulsation and frequency are actually the same phenomenon. It is just our perception that makes a distinction between something that is pulsating and something which is a pitch. Okay? So if you take a bass guitar and you really slow it down 10 times, you will get a pulsation. Tuk, 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 tuk. And if you speed up pulsation, you will get pitch. Okay? So those are technically the same things. So it is just our perception that makes it so radically different. Okay? So typically snare drum roll, fusing of events, you hear a texture rather than separate events. And then if you have high rate modulations, then it is quite clear how you get a difference in timbre arising from that. There is a transfer function for that. again, people meticulously measure how we hear stuff and draw graphs. That's 50% of psychoacoustics. Can be quite exciting. And one of the interesting things to note here is that MP3 compression is actually a psychoacoustically informed compression. So it's not like zip files where you have a numerical compression. It is the data can be expressed with less bits, but it actually has some information from psychoacoustics. Typically, one of the things is the modulation rates. So at different frequencies, you are not able to hear very fast undulations in amplitude of that frequency, and then you can reduce the bit rate there. And similarly, masking is also accounted for. So if you want to learn something about psychoacoustics, you can look at one of the books at the end of the slideshow, but you can actually look up all the bits in the MP3 compression, and you will learn a lot about what are the things that we don't hear. Okay? Because that's what MP3 is really good at, kind of reducing the data in that domain. Okay, temporal masking. So we've talked about masking in frequency domain, the fact that a low frequency loud sound will make a higher frequency soft sound inaudible. Okay? We have a similar masking phenomenon in time, such that a loud sound will make another sound inaudible if it comes after it, and believe it or not, even if it comes before. And that's the funny thing, again highlights this idea of having a temporal window of perception rather than having everything coming in as it happens, because I can play a short, soft sound, afterwards a loud sound, and I don't hear the soft sound that came before. Okay? Obviously, it's a bit more easy to understand how it happens that if I play a loud sound and then after I play a soft sound, I don't hear the soft sound. Okay? That's the forward masking, but actually the backward masking works as well. Okay? This is something you can test. Obviously, you can build these experiments in your audio editors as well. So I won't go into more detail here. It has to do with multiple things in terms of fatigue of your auditory nerves, in terms of your temporal window of perception, and other things. Okay, so here comes the second big chapter for today, which is localization. So we've discussed these basic perceptions of loudness, pitch, and time. And we've seen that they're all highly nonlinear. No matter the fact that we are quite, confident with the way we perceive sound, if you measure it, you realize, well, it's not quite precise. Now, with localization, what we have is a mechanism which is slightly more complex than the initial two ones, because it typically relies on the information in two ears. So everything we've discussed so far, you could do with a single ear, and localization relies on two ears, but there are some instances where people with a single ear functioning can hear some distinction in the sound source position. Okay, so that's quite interesting, and it has to do with the fact that filtering is one of the cues. But before I go to that, let's go one by one. So the first thing that allows us to distinguish position of a sound source is the fact that in two ears, this sound won't be equally loud. Okay, so it is the difference in level, interaural meaning between two ears, and that's fairly straightforward. If the sound comes from the right, it will be louder in my right ear than in my left ear. Okay, and that's a cue. And that processing that cue works automatically for us. So if something happens, someone plays the piano there, I don't hear the piano louder here and softer there. I hear the piano coming from my right-hand side, right? So this is a processing that happens subconsciously. You don't have any influence on this. So this interaural level difference works very well. It's an important cue for high frequencies, and that is because the shadow of my head, the acoustical shadow of my head, is much more significant for high frequencies. So likely you understand that high frequencies have very short period lengths, and therefore my head is an obstacle for a high frequency sound. Whereas a low frequency sound, which extends to quite a few meters, doesn't consider my head to be an obstacle. It bends around it very easily, and the loudness of a low frequency sound, the loudness difference, is much smaller. Okay? So if I have high frequency sounds, then the level difference is a very important cue. Okay? Now, if I have low frequency sounds, then the time difference will be more important in terms of assessing the position. Why is this? Well, if the waveform is really long, then the phase difference is actually quite dependable, right? So if you imagine a short wave length, okay, and then the size of my head, by the time it reaches the next ear, you really could have, I don't know, just the time delay will be crucial, will be much larger than the period of this waveform. Okay, so you cannot really establish a dependable phase difference in the right and the left ear, because it will be the multiple of the period duration. Whereas if it's a low frequency sound, then the phase difference will be crucially just a fraction of the wavelength. And there, the phase difference, the time difference, actually plays a role. Okay? So those are the two main mechanisms for hearing the position of a sound source. And as I said, you don't hear it coming earlier or later, louder or softer. It happens automatically. You hear it coming from here or there. Okay? Cool. The interesting thing about the interaural time difference is that you can perceive down to 10 microseconds of the time difference. And if you calculate that, that actually corresponds to much higher frequencies than what we hear. Okay? So the case is that if you record audio with a very high sample rate, you are not necessarily using higher frequencies, because you don't hear those frequencies, but you're necessarily using a higher time resolution. So typically, if you compare a 96K and a 44K recording, and it's a mono recording, it is very unlikely you will hear a difference. But if it's a lovely, lush stereo recording of a, dense soundscape or an orchestra, then you can actually hear the difference in the stage, how precisely things are localized. Okay? So our time perception is going to greater time detail. The interaural time difference is going to greater detail than our frequency perception in terms of the height of that frequency. So that's quite interesting as a finding, and obviously challenge it, do it, get a 96K recording, listen to it mono. Does the staging of your recording improve? Obviously, to assess the staging of your recording, you really need a decent set of speakers and a room and all the rest of it. Okay, so those are the differences that are crucial for perceiving local position. And then the other thing that we have here is filtering. So our pinny, these ear flaps here, they actually filter sound. And the fact is that they are quite asymmetrical, which helps us, which makes it so that the sound coming from different directions is filtered differently. And that is the crucial thing. So one obvious thing is that if a sound comes from the back, then it kind of hits an obstacle here. It kind of digs in there and probably gets absorbed most of all. So there is a definite difference between front and back. And more crucially, there is a huge difference between up and down. Because these two cues, they allow you to assess the azimuth of the position, so the left-right plane, but you actually hear a difference if a sound comes from above or below, right? So we hear elevation as well. Now, the way we hear elevation has everything to do with filtering of pinny. Okay, so you see that the ear flaps are asymmetrical up-down as well, and that's the crucial thing here. So what happens is that typically around 6-8K you will get different notches in the filtering characteristic, and as something moves up and down, these notches move. Okay, I don't have a graph here, you can look it up online, and it's something that you can try to play with as well. You know, when you're doing your mix, get a few notch filters in the area of 6-8 kilohertz, play with them, and what you might be able to do is space out your mix. Because if my hearing capacity reports something to come from above and something else from below, then I can actually distinguish better between these two sound sources. Okay? Try it. Try some notch filtering at those frequencies. The funny thing is that you can relearn these cues. So there are experiments where they modify the reflection characteristic of your pinny, and then initially you're confused, you don't know whether things come from above or below. Within a few days, weeks, you will relearn this new set of filtering characteristics, and you will be like, okay, it's fine again, I can hear things up and down. Then you remove it, you're back to your original ears, and you're confused back again. Okay, so the brain plasticity here is quite solid. You can relearn these things, which means that, I don't know if you know, but actually your pinny grow as you age. So there is definitely some things changing there, quite interesting. And then something that people tend to forget out of localization, which to me is the most important localization cue, is the turning of your head. I mean, it kind of works with these in tandem, but it really does help. So the fact is that as I turn my head, all of these cues are changing, but my sense of the position of the sound source does not change. This is a hugely complex neurological ability. Okay? Because all of these cues change, but I don't hear the position change. And that tells you how all of this is actually quite contextual as well. Right? So I know that this piano isn't moving, and that helps the whole subconscious mechanism keep it in place. So it is definitely the case that we have a lot of complex processing going from the basilar membrane into me hearing something, which is kind of a bottom-up processing. But the interesting thing about neurology is that there's a lot of top-down paths as well. So if I know in my consciousness that this piano is unlikely to move, I can actually measure this as well and create a set of unrealistic cue changes, simulate it moving, and I won't think it's moving. I won't perceive it moving because I know it shouldn't. Okay? So on top of this huge amount of bottom-up processing, there are top-down processes as well. Okay? And that goes to say something about the complexity and the impossibility of understanding it all. Okay, a few more things about a localization. We have something we call Haas effect, which has to do with precedence. And here you can measure this phenomenon. What it does to you, it makes you hear a sound coming from one direction, even though the cues are all saying it comes from the other direction. So typically what you have here is that one ear has a louder sound, the other ear has a softer sound. And then what you start to do, obviously you hear it coming from the louder direction, okay? And then you start delaying that position, that channel, and you still hear it coming from that side. So you actually play with the time difference and the level difference. And this is an interesting experiment to do because you get confused and you kind of start hearing things kind of quickly moving left and right. It kind of confuses your perception because actually what you're doing, you're creating a set of unrealistic cues. Okay. So I'm running out of time. I won't go to all the detail. One thing that you might find interesting if you're still running 32-bit audio unit effects, on my website I have one of them which is called Psychopan, which stands for Psychoacoustic Panning, where I use a lot of different cues to pan your signal. So typically you have the amplitude panning, you have the time delay panning, then you have the filtering panning, which has to do with the distance perception, and you have a decorrelation in there as well, which also has to do with your distance perception. And I thought there was a fifth one. So it allows you to pan things both left or right based on different cues, which allows you to confuse the listener. And the thing that I've discovered is that if you play these cues against each other, and if you use different cues for different sound sources, you get a much richer sound stage. Okay? So typically we pan things with amplitude, that's what mixing desks do, and we forget about all the rest, and my suggestion is try them. The problem can be mono sum, so if you're summing your stereo mix to mono and you have delay-based panning, it can mess things up, so beware. It's good to try it in mono mix as well. But in any case, there's so much more that we can do. And also in terms of distance. I think the paper from Gerzon that talks about the distance spot in digital mixers is about 30 years old now. Probably more, it was late 80s, I believe. So what you have is a guy who designs a distance spot and says, well, within a few years every mixer will have a distance spot. You know, just like you have left, right, you have back and forth. 30 years later, I don't really see them happening. Obviously, there are reasons for this as well, but it's again just that opening of the perspective. If you feel technically, talented and motivated, and you like the spaciousness of sound, there is so many things to explore. Okay, so what are the cues for us to estimate distance? Well, one thing is that it's learned, so you know how loud a scream is and you know how loud whispering is. And then if a whisper is very loud, louder than it's supposed to be, then you know it's very close. And if a scream is very soft, you know it's very distant, right? So there's a relationship between timbre and intensity that I've talked about, which also helps us estimate the distance of a sound source. Now, another thing that happens is that high frequencies roll off. That has to do with the transfer in mid-air. So the high frequencies suffer more. They attenuate. They get attenuated in air. The other thing is that the ratio between the reverberated sound, the reflections, and the direct sound is changing as well. Okay? So typically we call the position, this is interesting for recording, the position at which the direct sound is equally loud as the reverberant field, we call it critical distance. If you record something from further away than that, it's crucially different compared to something you record within the critical distance, where the direct sound is actually louder than the reverberant field. And these two, as you increase distance, will change, and that's another cue. Another thing is decorrelation. So actually what happens to sound as it reflects in the room or wherever it reflects is that you get slight phasing differences for the harmonics. And that's why if you have a synthetic sound where all the harmonics are perfectly aligned, you hear it kind of coming out from within your head. The distance is 0, right? And if you just play with the phase of your harmonics, you can actually get your synth to sound a bit more distant. And this decorrelation actually also contributes to your sensation of how large the sound source is, which is a really difficult thing to approach scientifically. So here you go, another interesting PhD topic there. And then familiarity of sound, I've just mentioned this. Okay, so those are the bits about the localization. I believe I've run out of time, so I'm just going to say briefly that there is a lot of science going into stream segregation, which actually has to do with you recognizing what happens in quick succession of different sounds. The lower level process there is called peripheral channeling, and the Gestalt principles that work for grouping visual stimuli, they also work for auditory stimuli. Okay? So we have here the proximity effect. So what happens is that A and B are different sound sources. If they are very close in time, you will hear them as two sound sources. If they're significantly far apart, you will hear it as one sound source going up and down. Just like you would group them here. You could actually imagine this to be one thing, especially if it doesn't say A and B, and here you definitely see it as two lines. Okay? Good continuation. Similarly, if there are two sounds, one after the other, if they have a continuation, then you will group them. Otherwise, you will think that they're separate sound sources. Similar things with closure. If you include gaps in the sound, you might hear that it has continued. You still tend to think it's the same sound source, same as in the visuals. And the interesting one, which is great for designing synths, is the common fate. So what I have here is a set of frequencies, and the ones that have the same amplitude modulation, they will group together. You will hear them as coming from the same sound source, and these other frequencies will group into a different group. So it is obviously quite complex. I invite you to dig into that. And then conflicting cues. What happens if I have two sound sources like this? Do I hear them as two sound sources going like that, or do I hear them crossing? And which parameters allow me to hear which version? So just the highlight of this being very complex. And then I won't talk about listening test methodologies. If you're interested, if it's going to feed into your final year project, look it up. And then finally, the end of the slideshow is a whole bunch of references, something online. There's really good stuff online in terms of lectures. Okay, so these are lectures, these are lectures, these are lectures. Tons of YouTube stuff as well. So if anyone's interested, you should be able to find myriad interesting sources. Awesome. If there are no questions, any questions? Cool, thanks for coming, guys, and catch you later.